All right, so for the chemical engineers in the class, I kind of assume that you already have taken thermodynamics, and this is going to be more of a review. For the chemistry majors, sorry, you're laughing. So for the chemistry majors, I'm going to go over the key concepts we're going to need. Again, some of this, the key concepts you've learned when you're taking high school and freshman chemistry. So some of the stuff is just going to repeat here. But my goal in this chapter is just to sort of establish the language that we need to learn statistical mechanics. So what we're going to do is take that microscopic picture and translate that into macroscopic properties. So particularly for the chemical engineers, that's the most important part, I think, about this class is how, you ask, like, why are we learning all this quantum mechanics? And the reason is because that quantum mechanics is what determines the macroscopic properties that you're working at, and statistical mechanics will be that connection. But before we do that, we have to go back and review some of the language we're going to use in thermodynamics, okay? So again, we have an hour and a half. It's a lot of material I'm going through in this lecture, but stop me, raise your hands, particularly you guys who already understand this if you want clarification about some of these concepts. Now, thermodynamics really it's completely phenomenological, and it starts with the basic idea of the conservation of energy, which is the first law of thermodynamics, that all energy is conserved. So that is going to be really all you need to derive everything, like even including concepts of entropy. But we're going to work through exactly how that all comes about. Okay. So again, it's a lot of this is about vocabulary, just getting it clear, because when I use certain words, I'm going to have very specific meanings in thermodynamics, and it might be different than what your everyday meaning of that word is. So just keep that in mind. There's very specific meanings to these terms, okay? So we're going to be talking about states of matter, and we know that matter can come together. We've been talking about gas phases. We know that there are electrostatic attractions between molecules that will bring those molecules together in the gas phase to form liquid phases, and then continue down to form solid phases. So we'll be talking about solids and fluids in thermodynamics. And when we talk about the distinction between the two of them, solids can withstand and hold a shear stress. So you can apply a shear stress to a solid and it will sustain that. Whereas a fluid will flow under a shear stress and won't be able to sustain that. And then within the realm of fluids, we'll be talking about liquids, gases, and also plasmas, but mostly liquids and gases, okay? I'm hoping that those are pretty clear concepts already in your mind, okay? Now, another important thing that we need to be clear about when we're talking about thermodynamics is what do we mean by the system that we're working on and the surroundings that it's interacting with, okay? So the system is some macroscopic part of the universe that we're looking at, and the surroundings is everything that interacts with the system we're looking at, all right? That part, I think, is pretty straightforward. We also are going to have a number of adjectives for describing the boundaries between the system and the surrounding. And those boundaries are going to regulate the flow of energy and matter between the system. So if we say that the boundary is permeable, then I mean that the boundary allows matter to flow between the system and the surroundings. Okay? If it's impermeable, then no matter can flow. The system can do whatever it wants, but no matter can be exchanged between the system and the surroundings. Right? Sometimes you'll have semi-permeable boundaries. For example, in batteries, you'll have a semi-permeable membrane that might prevent the cathode and anode materials to go mix, but maybe electrolytes to go back and forth. We will also have diathermal boundaries. Diathermal boundaries will allow heat to flow from the system into the surroundings and back. Adiabatic boundaries are the opposite of that, like your thermos mug or your coffee. Those prevent heat from flowing between the system and the surroundings. And then the last one here we're talking about is rigid boundaries. And rigid boundaries are boundaries that prevent the system from expanding or contracting, so that we prevent all expansion work between, on the system, or the system doing expansion work on the surroundings. Any questions about those adjectives? All right, good. We're all on the same page. Oh, yes. Finally, an isolated system. When I say an isolated system in thermodynamics, I mean a system that has impermeable boundaries, adiabatic boundaries, rigid boundaries, no energy or no matter can flow between the surroundings and the system, right? So that's a very strict definition when we mean isolated system, okay? And when you say, oh, I'm feeling really isolated today, that's not in the thermodynamic sense, because you would be dead very soon, because no energy or matter will be able to flow between you and the surroundings, okay? So isolated in thermodynamics means something very specific, okay? So when I say an isolated system, it's very constrained, okay? All right, so what do we mean when we talk about equilibrium, systems being at equilibrium? And in fact, actually, all of thermodynamics is about equilibrium states. And the process of going between equilibrium states can involve non-equilibrium processes, but as long as we start and end at an equilibrium state, then we can talk about, which direction it will go and other types of thermodynamic properties. So obviously, an isolated system is going to be at equilibrium when all of its properties stop changing in time, right? You've got a system that's isolated. You wait until the temperature gets constant, the pressure gets constant, uniform throughout. That's going to make it. That's when it's going to go into equilibrium. That's pretty easy. But what about if you have a non-isolated system? So a system that's in contact with its surroundings. Maybe it's exchanging energy with the surroundings, or it's exchanging matter with the surroundings. How do you know when that is in equilibrium? And the way to know that is if you know that the macroscopic properties are time independent, just like in an isolated case. But if you took that system, which was interacting with the surroundings, and you made it an isolated system, and the properties continued to stay constant in time, then it was a system at equilibrium. Okay? If it removed from the surroundings, the properties start changing, then it was probably some kind of steady state process where matter is flowing in and out in such a way that it appeared to be constant, but it was not constant when you isolated it. Okay? All right. We're going to be talking about state functions in thermodynamics, and those are the macroscopic properties that depend only on the system's current equilibrium condition. So it doesn't depend upon the history of how you got from state A to state B. It only depends upon, I'm in state B, and it doesn't matter where I came from, A, C, E, states, whatever we want to label them, I'm in state B. Those state functions are going to be the same as long as I'm in state B. It's independent of the history, all right? Now, these state functions, these macroscopic properties, we're going to be working with properties that can be often classified, not always, into two categories. One is extensive properties, where they depend linearly on the amount of substance you have, and intensive properties, where they're independent of the amount of substance. So if you think about extensive properties, imagine a system, you make a complete clone of that system, perfectly duplicate, and then you put them together. If the property in question doubles in value, then that was an extensive property. But if you make a complete clone and the property stays exactly the same, then that was an intensive property. Okay, this is a quick rule on how you can work that out. All right. We're also going to be talking about thermodynamic phases. So we've talked about the states of matter, solid, liquid, and gases, but when we're talking about a thermodynamic system, we'll talk about how many phases are in that system. So by a phase, we're going to be using this language here. We're going to talk about any region of space where all the properties, all the intensive properties are constant throughout space. That's called a uniform region of space. Right? A homogeneous region is where the intensive properties vary continuously through a region. So they're not constant, but they're varying continuously. And heterogeneous is where the intensive properties will vary discontinuously, okay, throughout the region, right? So you imagine Lake Erie right now, okay? Lake Erie, is that a uniform system or a homogeneous system or a heterogeneous system? what would you call it right now? I don't know what today's pretty warm, okay? So maybe there's not ice floating on Lake Erie, but maybe there is. If there was ice floating on Lake Erie, then you'd have liquid and solid together. You have discontinuities in the properties like the density and molar volume and things like that. So that would make Lake Erie a heterogeneous system, right? But if I have a glass, same if I have a glass of ice water, that's a heterogeneous system. But if I just had a glass of water, it was all at one temperature, it's been sitting there for a while, it's probably uniform. Okay, so keep those in mind. So we're going to define a phase as the region where all the physical properties are homogeneous, right? So if you have a heterogeneous region, then obviously you're moving from one phase to the next. Okay, so you can have multiple phases in your system. That's going to make it a heterogeneous system. Okay? All right, so we want to describe this macroscopic object. Now, so far in this class, we've been thinking about the systems, the materials, the gases or solids or liquids, from the completely microscopic point of view. And you know, from a microscopic point of view, if I have a mole of atoms, that's 10 to the 23rd position coordinates, x, y, and z coordinates, 10 to the 23rd px, py, and pz coordinates. That's a lot of coordinates to describe that system. In thermodynamics, we're going to describe it with a very small set of parameters. So we're going to have, say, n parameters, n state functions that are going to completely describe the equilibrium system. And n isn't going to be 10 to the 23rd. It's going to be a small number, just a few, maybe a handful or a dozen, depending on the situation, which is really amazing to think that you can describe the equilibrium state of a system by just a handful of parameters. And those handful, I'll call them n, depending on the situation, from those n, all the other properties can be derived. So we'll say that we're going to pick n properties. We're going to pick n independent properties. We're going to label them x, x1, x2, x3, x4. You can imagine from thermodynamics what those could be. And then every property that's not included in that list can be calculated from that list of n properties. And the relationship of the properties that we're getting from this original n is what's called an equation of state function. So for some equilibrium state, you can calculate any property of the system from some core set of n parameters. Like I said, it's kind of amazing this work, but it has to do with sort of the statistics of 10 to the 23rd particles moving around, right? It's like me knowing that the average in this class is going to be something, because I've taken the class, teaching the class so many times, I know the average is always somewhere around this particular number, right? Even though everyone varies individually, the average is the same. It's the same thing in thermodynamics. When you have that many, I can't imagine teaching 10 to the 23rd students, right? But if you have that many students, then you imagine that those averages are never going to change, right? That's what an equilibrium state is. Okay, so these equation of state functions, I said I'm going to pick n independent parameters, and then we'll calculate everything else from them. Which ones you pick really depends upon the system. This is why thermodynamics sometimes can get a little bit confusing, right? Because we've been talking from a microscopic point of view. There's no question. We need to know the positions and momentum of everybody, and then we can go forward, right? But from thermodynamics, it's not the same. You say, I need n independent state functions, but which ones I pick really depends upon how I set up my system and surroundings and the boundaries. So that's going to be the influence in what's the natural choice for those variables. You might be thinking pressure, temperature, energy, entropy, there's all these variables. How do I know which ones to pick for the end? It should become apparent to you when you see how you set up the system and how it's interacting with its surroundings. Okay? That should be clear by the end of the lecture. It may not be clear now. Okay? So these equation of state functions, for example, if I have a pure substance and I have diathermal boundaries, so it can exchange heat with the surroundings, but I have non-rigid boundaries, so the volume is fixed. So if I have that kind of system, then what are going to be the natural variables will be the pressure and the temperature, right? And so I can say that the volume will be a function of the temperature, pressure, and the number of moles of that pure substance. So these are my n variables, and volume is the dependent function. But I could have had diathermal boundaries. Sorry, this was non-rigid. I meant to say up here. This was non-rigid. So I have P and T, and that would give me this equation. If I had diathermal and rigid boundaries, then V would be constant, T would be constant. Then I would use this as my equation state. I would pick T, V, and N, right? So rigid boundaries with constant T and V, I would use these guys. If it was constant P and T, I would use these guys and calculate V or calculate P. Okay? It was just the choice of what I held constant in determining how I picked my N and how I figured out what my equation of state is going to be. So examples you'd be familiar with, the Guido gas law, Van der Waals equation of state. These are all equations of state that relate some dependent variable to the independent variable. And of course, that's a simple one substance system, single phase. If we had multiple substances, then you're going to need, for every substance that's there, you're going to need 2 plus S n independent variables to describe it. So for example, if you had S independent variables, and you need T, V, N1, N2, N3, all the way up to NS, for example, in this case, or in this case, you would use the same kind of thing, right? Any questions here? Does this look familiar to you guys? I'm putting it in a very general context, okay, just to get the language clear. So this is really kind of like the executive summary of thermodynamics you're getting. All right. Now, we've talked about the system in equilibrium and all those adjectives we want to use to describe the system and the surroundings. But we're interested in moving the system from one particular equilibrium state to another equilibrium state. And that process of moving it is going to be described with a number of adjectives in thermodynamics. So even more vocabulary that we want to get clear here. So when I say that I have a process that's an expansion or a compression process, well, that one's kind of obvious. It means that if it's an expansion process, the volume gets bigger as the process goes from A to B. Or compression, the volume gets smaller. That's sensible. If it's an isothermal process, then what I mean is that the temperature remains constant and uniform throughout the process from A to B. Okay, so let me be clear about that. I'm not saying only that A has the same temperature as B. I'm saying that as A transforms all the way to B, the temperature remains constant and uniform throughout the process. Okay? That's a much more strict definition than just saying A and B have the same temperature. Okay? That's isothermal. So likewise, when you see that the process is isobaric, baric is related to pressure, constant pressure, that means that the pressure has remained constant and uniform throughout the process from A to B. Okay. Isochoric just means that the volume remained constant throughout the process. Adiabatic means that no heat was allowed to flow during the process. Now, so we have adiabatic boundaries. Obviously, adiabatic boundaries will enforce an adiabatic process. But if no heat is allowed to flow, that's called during the process, that's called an adiabatic process. We can also have cyclic processes where we start from A, we go through some path, and we come back and we end at A. That's very important for engines. You know, engines, when you're building an engine, in a thermodynamic engine, you want to go through some process, and then you want to come back and you want to repeat. And in that process, you might generate work, or maybe it's a heat pump, and you're moving heat from a cold reservoir to a hot reservoir. And then the last one is reversible processes, where we're infinitesimally close to equilibrium throughout the process. And this one is going to take a few graphics to get clear. But any questions about these first ones up here? You guys have seen these before, but you understand I'm making very clearly how some of these are very strict in what they mean in terms of what the process is. All right, so let's talk about what reversibility means in thermodynamics. So I didn't have time to make really pretty graphics, so these are my hand-drawn graphics here. So When I'm talking about a reversible process, I mean that the system is at equilibrium at every point. When I'm going from A to B, every point along the way, we are at equilibrium, right? So what does that look like? So if I took a system and I cooled it from, say, 20 degrees to 0 degrees, and I did it reversibly, then you would imagine the system at 20 degrees at equilibrium, it's uniform, it's 20 degrees throughout. Okay? And then I maybe put it in the bath and I cool it down to like 19.999 degrees. And I go so infinitesimally slow that at every point during that process of cooling, you look at the system and it's uniformly that temperature throughout. Now, you contrast that to an irreversible cooling process where, say, I had a system that was sitting in a 20-degree temperature bath, I had equilibrium, all happy, and I pull it out and I plunge it into this cold bath, right? You can do that, like, in Finland, like you go into the hot sauna and then jump into the ocean, right? Yeah, that's an irreversible process for sure, right? So you throw it into the cold bath. What does the temperature look like in this system as it undergoes this transformation from this state to this state? Well, you know what's going to happen. So initially, it's going to cool on the outer edges, right? In the core, it's going to stay warm, right? But then as it cools, the outside is going to get colder and colder, and the core inside that's warm is going to get smaller and smaller and smaller, right? Until finally that cooling goes all the way through and it's all at equilibrium at the new temperature, the lower temperature, right? Imagine that process the other way around, where we took it from a cold bath and we plunged it into a hot bath. What would the temperature gradient profile look like during that process? It's not going to look the same, right? It's going to be hot on the outside, cold in the middle, and then it's going to change. You can always see that a process is reversible because if you had a movie of it and you played the movie backwards, it would look crazy, like nonsense, right? The person just like, magically like falling to the top of the building or something, right? That's not going to work, right? So you can see a process is irreversible because if you play the movie backwards, it looks impossible. But a reversible process, if you played it backwards or forward, you really can't tell, right? Okay, so that's clear. Is it clear? Okay. The same thing with compression and expansion. I can do reversible compression, and if I do reversible compression, I'm pushing this piston in infinitesimally slowly so that anywhere inside the cylinder, the gas is at equilibrium. The gas is uniform pressure and constant throughout here, right? And I'm doing this compression infinitesimally slowly, and I'm always at equilibrium. But if I did this irreversibly, if I took the piston and I pushed it in pretty fast, then what's going to happen? Well, what's going to happen is that as I push it in, the pressure is going to be higher right behind the piston, right? Because there's going to be a dense region. As I push it in, those molecules aren't going to have time to get away, and they're all going to get crowded, right? It's like at a concert, when everyone rushes to the front, right? Suddenly there's this wave of density, right? Moving it, so they're all running to the stage, right? So you're pushing this in, and so you have this dense region here, and as you keep pushing, you see that this wave of dense is different from this over here, where it hasn't quite faded there. In fact, actually, the time scale for this guy to come to equilibrium is on the order of the speed of sound inside this particular gas, right? So you can imagine irreversible compression played backwards is not going to look sensible. Similarly with irreversible expansion, if I reduce the pressure on the piston and it comes out, then we know that there's going to be the opposite. We're going to have a low pressure region right behind the piston, and that far away from the piston will be higher in pressure. Okay. All right. So now let's talk about work in thermodynamics. Now we've learned about work in chapter 1, how to calculate work. We know work is a force applied to an object, moving it through some displacement. So that part we're all good with now, I hope. So we know that work in thermodynamics we can write in terms of minus PdV. You can work out the pressure, and you can say that the work, differential work, is just minus PdV for a piston that's being expanded or compressed. But in general, there will be all kinds of ways in which you can do work on a thermodynamic system that involve other macroscopic coordinates. So we're going to be looking at not just PV work, where you could, not in this class, but you could be looking at other than PV work. You could be looking at the work associated with magnetizing the sample, or charging a capacitor, or changing the surface area of an object. So all of these processes can end up putting energy in and out of the system. And so we're going to just sum all them up. We're going to say that there are beta ways in which we can do work through beta different macroscopic coordinates. So we have some kind of generalized force. So pressure is an example of a generalized force, and volume is an example of a generalized displacement coordinate. Okay, the forces will tend to be intensive properties, and the displacements will tend to be extensive properties. Remember, intensive properties are independent of the amount, extensive depend on the amount. Okay. Again, this is the thermo-executive summary. Okay, so here are not everything, but a good bit of some of the different types of work that we can do on a thermodynamic system. So obviously, this is the mechanical work, pressure, PVDV work. There's also elastic stretching, or a rubber band, for example, compressing an elastic object. That's elastic working. That's surface area. So like blowing up a balloon, you have the work that you put into expanding the surface of the balloon. That there's a surface expansion, a surface area that's increasing, and it depends on the surface tension, which is surface tension times the change in the area. For chemists, we're also interested in chemical work or transfer work. So that means that if we have transfer, like moving from solid phase to liquid phase, or gas phase to solid phase, there is a work associated with that, where N is the number of moles you move between phases, and this mu is something called the chemical potential. That's the generalized work, and the number of moles is the displacement. All right. You can do that with reactions or phase transitions. It's the same thing. This is what's called a materials type work in thermodynamics. And then, as I mentioned earlier, the other types of work you can do involving charging the sample, magnetizing it, polarizing it. All of those things are ways in which you can put energy into the system or take it out into the surroundings. Right? Any questions there? Yes. So this is the coordinates being displaced, and this is the generalized force that's causing the displacement. Does that make sense? Okay. You can stare at this for a bit. You probably only ever work with the top ones, right? But there are all ways in which you can sort of grab hold of some macroscopic coordinate and do work on the system. All right. Well, let's look at why reversible processes are important when you're talking about work in thermodynamics. So we talked about this compression of a gas, right? And when it happens reversibly and irreversibly. So if I'm doing reversible compression, then the gas inside here is always at equilibrium throughout the process. And if I was doing expansion, it would always be reversible expansion. It would always be at equilibrium. So the pressure that's outside, the external pressure, and the pressure inside, the equilibrium pressure of the gas, are going to be equal to each other all throughout the process. So if I plotted the pressure versus the volume, I plotted to say, actually I didn't get to change this in time, let's say that's the external pressure. If I plotted the external pressure versus the volume throughout the process, whether it was compression or expansion, if it was done reversibly, it will all go on the same line. And of course, the work is just the integral of PdV. So that means that work is just the negative of the area underneath this curve. So this is really handy when you're looking at these PeV curves, because whenever you look at a process, you look at the area under the curve and say, well, the work is the negative of that. Okay? So in a reversible expansion and compression, the work you put in is equal to the opposite to the work you get out. So it's like, you know, in a sense, you know, you're charging your battery, so to speak, right? You put work into compressing the gas reversibly, and then later you want to get it out, you reversibly extract it out, you get everything you put in. Great, right? Now, what happens if you have irreversible processes involved, right? So if I was compressing irreversibly, then the pressure over here is not going to be at equilibrium, and I'm going to have this higher pressure behind the piston. So what the external work pressure is seeing is a higher pressure than what the equilibrium pressure would have been if I had done it reversibly, right? If I was trying to compress this reversibly, I would see a lower pressure than what I would see if I was compressing it irreversibly. By pushing it in, I got this higher pressure here. So that means that in that process, if I was compressing it from this state to this state, from a larger volume to a smaller volume, along the path, the external pressure, that should be P external, the external pressure would move along a path so that the area under that was greater than what it would have been if we were doing it reversibly. That means I had to do more work to push it in irreversibly to get between the same two states than if I did it reversibly. Okay? So that's bad. Obviously, you guys are engineers. You know, that's bad. I don't want to do more work than I have to do, right? So I should have done it reversibly because I spent more work trying to overcome this non-uniform pressure. What about expansion? So if I want to get the work back out of the system, well, if I'm expanding, when it's expanding out, there's going to be lower pressure here than what the equilibrium pressure would be. And so there's going to be higher pressure over here, lower pressure here. And so as this expansion takes place, then we're going to be going from here, this volume to this volume. We're going to be feeling a smaller pressure. So we're going, as that we're doing work on the surroundings, we're going to be coming along a path from here to here, which always has a lower pressure than what the equilibrium pressure would have been. So that means the area under this curve is less, meaning I'm going to have less work that comes out if I expand it irreversibly. So that sucks, because if I go in irreversibly, I put more work in, and if I come out irreversibly, I get less work out. And so it's not good, right? If I do it reversibly both ways, I'm going to get the same what I put in and what I put out. But you can see here then, because of this simple picture here, that the irreversible compression is going to be more work than what you're going to get out for expansion. Any questions about that? This is really important. Assume you guys have seen this before, but maybe not. Yes. How can I tell I have less pressure? Because the work is the negative of the area under the curve, right? So if the reversible path is here, and the irreversible path is this. I'm sorry, going expansion, right? Here, it's coming out. It's always lower, right? Because the pressure behind the piston is always lower than what the equilibrium pressure would be. Then that means the area under this curve is always going to be less. Right? Again, that should have been P external. I didn't get a chance to change that, so that's what we're looking at. From our point of view, we're getting work, we're putting work in, we're taking work out, and that's us out here. Okay. Any other questions? Okay, is this making sense to you guys? All right, so now we move on to heat. Now, heat is something we haven't really talked a whole lot about, although we've talked about temperature and what temperature means. But from chapter 1, we learned that the only way you can get energy in and out of a system is through work. And that's still true. But in chapter 1, we were thinking about the positions and momentum of every single particle in the gas. And now we have in thermodynamics only the macroscopic coordinates that we can do work on. So any work that you do any sort of, I'll call it any chapter 1 work that you do on the gas that doesn't lead to a displacement of a macroscopic coordinate, that's heat. Okay? So from chapter 1, heat is just work that you can't see on a macroscopic scale. Okay? So that part, I don't know if you know that. Maybe you talked about heat before, but just make sure that you understand that, okay? From chapter 1 point of view, there's only work. You can only apply a force on a particle and move it, right? But in thermodynamics, the only work we can see is what we call thermodynamic work. And that leads to some macroscopic displacement. But the energy that's moving in and out, it has to be going in and out like chapter 1 work. So what we're saying is that all that work, chapter 1 work that we put in and out, that doesn't lead to a macroscopic displacement, that's all grouped together as heat. Okay? Clear? Okay. Something you also know, of course, is that if you put heat into a system, its temperature will go up. When you take heat out, its temperature will go down. And the quantity that determines that characteristic, how much, is called the heat capacity. Okay. This is defined in the absence of all possible thermodynamic work. Because obviously, if you're doing work at the same time, then it's going to complicate this quantity, which is the heat capacity, right? So when we talk about heat capacities, sort of implicit is this idea most of the time that you've stopped every other process and you're only putting heat in, and there's no phase transitions, no chemical reactions, no other type of work that's taking place, right? I'm grouping chemical reactions and phase transitions in the category of thermodynamic work. Okay, here we are, the first law of thermodynamics. That was just my review of the vocabulary. Any more questions about those terms? So, in chapter 1, we learned about the conservation of energy. That still certainly holds true in thermodynamics. So we know now that heat is just microscopic work, right? So if we have a full counting of all the heat and thermodynamic work that's going in and out of the system, it should all be accounted for, and we won't have any energy unaccounted for. So the way we write that in the differential form is that du, which is the change in energy of the system, is equal to these inexact integrals of dq and dw, where this is the heat flow and that's the work that's done. Now, I don't know what you guys do in chemical engineering, but do you have the opposite sign for your work? So is yours dq minus dw? Good, good. That makes things a lot easier. Because some of the older books will they have the opposite sign because they think of work as what you get out of the system, but we use work in the sense that if work is negative, that means the system lost energy. If work is positive, the system gained energy. Okay, that's our sign convention. So energy is a state function, which means it only depends on the initial and final state. But heat and work depend upon the path that we go through, right? We've already seen examples of that with work because we saw that whether we're doing reversible or irreversible, the work is different, right? Depending on the path that you chose. But the initial and final states have the same difference in their internal energy if they're at equilibrium. So that's the most important thing. And then this sign convention here, I just want to be clear because different fields will sometimes treat work with a different sign. Now, heat capacity, I mentioned before, but I'm going to be rigorous about how I define what a heat capacity is here. So if I do not allow any kind of work, the system to do any kind of work, so I prevent, I put all those boundary conditions in so there's no kind of work can happen. And then I measure the change in the energy with all that work fixed so it can't happen. Then the change in the energy with respect to temperature, du dt, is what's called the heat capacity. It's actually called the constant volume heat capacity, which to me seems like a bit of a misnomer. because it's a no work heat capacity. So even though it's constant volume, so there's no PdV work, it actually implies much more than that. It means that there's no other work that's happening. But the textbooks tend to not actually mention that little detail, and it can lead to a lot of confusion, obviously. So, but it's called CV, but it means no work is allowed. It means no phase transitions, no chemical reactions, no magnetization, no polarization, no charging, discharging, none of that stuff has happened. This is purely the effect of putting energy in and seeing the temperature increase or decrease, or decrease if you take energy out. Okay. Now there is another quantity. Actually, there's lots of thermodynamic energies that we're going to be dealing with here. And the first one that we're going to come to beyond the total energy, the internal energy, which is called the enthalpy, which you probably remember. And enthalpy is a state function that's been put together for people who like to work under constant pressure conditions, which is how we work in a 1 atmosphere kind of world, right? We have a reaction on a benchtop, it's constant pressure, 1 atmosphere, right? We don't usually do our reactions in sealed vessels, but sometimes we do, right? We might do it in a constant volume vessel, but oftentimes we do it in an open reactor where the pressure is constant, 1 atmosphere of pressure, right? So this turns out to be an important state function because if you define U, it's in terms of other state functions. Then if you do the differential during a constant pressure process, then du becomes, dH becomes du at constant pressure plus PdV, okay? Because pressure is constant, so you do the derivative with respect to the product rule, the P part goes away, the dP part goes away. Now, remember that du is just the heat and the work was all those other ways in which we could do work, right? So I'm going to pull out of that list of all those other ways to do work, I'm going to pull out the PdV. So this is all the ways you can do work, including the PdV, but then this definition of enthalpy adds PdV to the end. So you can see that this PdV is going to cancel out that PdV, and so enthalpy is going to end up being dQ plus all the work except PdV. So then, if you make sure that there's no other work besides PdV, so you make sure that there's none of this can happen, then that equation then simplifies to that. And we can then say that the heat flow, which is a path function, during a constant pressure process is going to be the enthalpy change during that constant pressure process. And that's going to be just Cp dt, where Cp is defined as the partial H partial T at constant pressure. Although constant, this P down here, not just means constant pressure, it means constant pressure, and every work except for PdV work is held fixed. Any questions? All right. So let's look at calculating work and when a gas expands. And we're going to look at 3 cases here because they're going to turn out to be useful a little later on. But we know work is this path integral here, and we're going to do it for an ideal gas. So for an ideal gas, we know that pressure is nRT over V, in the equation of state, right? We're going to look at 3 cases. We're going to look at isothermal reversible expansion, so we're in equilibrium throughout the process. We're going to look at adiabatic reversible expansion, so we're again at equilibrium throughout the process. And then we're going to look at adiabatic irreversible expansion of an ideal gas into a vacuum, where we won't be at equilibrium throughout the process. So these are going to be 3 useful derivations where the result will be used later. We want to keep in track what they're going to tell us some important physical concepts here. Okay, so if we start with the easiest one, which is the isothermal case, well, that's nice because since it's isothermal, temperature is constant and it slides out of that integral. If I go back to the previous slide, here it's inside the integrand, but because it's constant, it can slide out. That's great because then my integral is just dV over V. Piece of cake, right? You know how to do that? That integrates to minus nRT log of V final over V initial. So that's the work that happens during reversible isothermal expansion. And since temperature is constant, delta T is constant, it's isothermal, right? What did we learn in chapter 3 about an ideal gas, the energy of an ideal gas? How is energy of an ideal gas related to its temperature? In chapter 3, we learned that it was 3/2 RT, right? Was the energy of a gas. 3/2 RT, right? If temperature is constant, if delta T is constant, what's delta U? It's 3/2 R is the only other numbers, variables in that. They're not really, they're constants, right? So it has to be 0, right? So if delta T is 0 for an ideal gas, then delta U has to be 0. And if delta U has to be 0, then the first law tells us that Q plus W has to be equal to 0. And if you do this work, and to maintain delta U of 0, the heat has to be equal and opposite to the work. So if you do an isothermal expansion, which means you have your piston cylinder in a constant temperature heat bath, or constant temperature bath, and you do work and you let it expand out, the work that you get out, the energy of that work is reabsorbed through heat back into the system, because the system has no change in energy when it's done. Okay? That's important to keep in mind, right? So I'm expanding a gas isothermally, it's in contact with some temperature bath. So as it expands, it does work on the surroundings, but it's also sucking heat in so that it maintains a constant energy. All right? Good. Now, this one's a little trickier. What if we want an adiabatic expansion? So we take the piston cylinder out of the bath, so now it's got a thermos around it, so there's no heat that can go in and out of it. And we want to work out what that process is like. So obviously, if it's adiabatic boundaries, there's no heat flowing. So it's just going to be the work. du is going to be equal to the work. So, okay, fine. We need to calculate the work, but because temperature is going to change, so if we go back over here, go back to here, if we're doing this adiabatically, you see that if the system's doing work, then it's losing energy. If it's losing energy, its temperature is going to go down. If its temperature is changing, we can't slide that T out of the integral, right? So how are we going to do that integral if we can't slide it out of the T out of the integral? So this is what we're going to do. Okay, so this is a few reveals. So first of all, we know that there's no Q, and all we have left is du is equal to dw. Well, du is equal to CV dt, right? Okay, that's from our earlier definition of heat capacity, which is of course equal to work, which is equal to minus P dV. The equation of state for the ideal gas tells me that this P can be replaced with nRT over V. So I'll just go ahead and substitute in there. And then I'm going to integrate both sides. I'm going to rearrange, pull the T's over to one side, put the V's over here, pull everything out that's constant, and I'm going to have this integral here for both sides. This integral is just dt over T. If I assume that CV is independent of temperature, which is not always true, particularly for real gas, but over a limited range can be true. So we'll just assume that this is independent of temperature and it slides out of the integral, and that just becomes CV log of TF over T initial. The M means molar heat capacity here, so I just added that in. So we're working with molar heat capacities. So I divided by N, CV over divided by N is the molar heat capacity. And then on the other side, that integral is just simply minus R log of V prime over V initial, right? So then I'm going to do a trick, and it just seems like I'm pulling this out of a hat, but I know from an ideal gas that the difference between Cp minus Cv is the heat capacity. I'm sorry, is the gas constant. So this difference in heat capacities is the gas constant. So I'm going to replace this R with the difference in those heat capacities for the ideal gas. And that allows me to rearrange this guy, so I can bring this over to the other side, so I get this expression here. And then I'm going to define gamma, which we've actually already seen in the in the wave chapter as the ratio of the constant pressure and constant volume heat capacities. And that allows me to rearrange this into this form. Okay, there was a lot of steps here to get it to this form, but this is what happens during adiabatic expansion. We know that you have a volume change, you're expanding, volume is decreasing, and we know the temperature is dropping, right? So this tells us the ratio of the initial to final temperature to the ratio of the initial to final volume. Okay, that helps us figure out what's happening, and it requires the ratio of the heat capacity for the ideal gas. You can actually then use the equation of state for ideal gases to actually convert that with pressure. You can use this guy here, and you can rearrange it to get PIVI to the gamma is equal to PFVF to the gamma, and that's adiabatic expansion. And if you remember Boyle's law was isothermal expansion. Boyle's law was PV is equal to PIVI is equal to PFVF, right? That was Boyle's law, isothermal expansion. Adiabatic expansion is PIVI gamma is equal to PFVF gamma. That makes it a little bit easier to remember, right? Just raising the volume to the ratio of the heat capacity. And then, of course, finally, we can get the delta T from just rearranging that expression. And if we wanted to, we could get the work, but you might have forgot that was what we were after at the beginning of this. We can get the work by just integrating the difference in the internal energy, and we get this expression here. So that one was more involved than the isothermal expansion. So the adiabatic expansion was trickier, but it's a very important result. We're going to need this when we want to understand the Carnot engine and how entropy was discovered. Okay. All right, how you guys doing? We've been at this for not quite an hour. Had I bought a hot water? All right. Okay, the last one we were going to talk about here in these three is what is the work done if I had a glass bulb with 2 atmospheres of a gas, say an ideal gas, and connected to a vacuum, equal volumes here, and I have a nozzle here where I can turn and allow the gas to expand into the other side. This gas expands into this vacuum. What's the work that the system does in this expansion? Raise your hand if you know the answer. Raise your hand if you don't know the answer. Okay. Who raised their hand if they know the answer?
It's 0, isn't it?
I think it is 0, isn't it? It is. Why is it 0?
Spontaneous is pressure value work, but you're not really changing internal based on the system, and the volume stays pretty much the system.
Well, I think there's a simpler explanation, which is what's the external pressure?
Oh, pressure, external pressure is 1 atmosphere.
The external pressure here.
Oh, external pressure 0.
And what's the external work? If the external work is PdV, right? And if P in your PdV, P is 0. You can't do on any work, right? So in other words, if you're gas and you're flying into this region here, who are you displacing? As you move in it, no one, right? So there's no work in this expansion. Everyone see how that happens, okay? This is really important. If a gas, an ideal gas expands into a vacuum, it does no work. And this is all adiabatic. There's no way for heat to go in and out of this. But if there's no work, and there's no heat flow in this whole system, what's the change in energy of this ideal gas? 0, right? Okay. So even though its volume doubled, it looks like, okay, you think intuitively, okay, I just did an expansion, I'm going to do work, but you're expanding against nothing, so you do no work, right? So the internal energy change is 0. It's an ideal gas. What's the change in the temperature? An ideal gas, if the energy change is 0, what's the temperature change of the ideal gas? zero, right? Because the energy of an ideal gas is just 3 times RT, right? Now, a real gas, on the other hand, will change its temperature when it expands into a vacuum. Have you guys ever heard of the Joule-Thomson effect? Okay, so that's a way of exploiting the fact that a real gas, so if we're gas molecules that are in the gas molecules over here, when they expand into the vacuum, there's an interaction with other gas molecules. And so if you remember the potential energy surface of interaction between molecules, we looked at in electrostatics chapter that there's an energy of interaction and there's that potential energy surface. And if they're on that surface, say they're at the equilibrium distance, away from each other, if they go into the vacuum, then they move further away, they're moving up the potential energy surface. That means that their kinetic energy is going to decrease. That means the temperature is going to decrease. Okay? If the kinetic energy decreases because they moved up in potential energy, then the temperature would go down. So a real gas can actually cool on expansion. On the other hand, if they were really tightly packed in here, and they weren't at the equilibrium distance in that potential energy surface, they were in the steep part where they were too close, then when they expanded, they actually would drop in potential energy and move down to that lower point. So they would actually increase in their kinetic energy. So they would actually heat up when they expanded. Okay. So gases, real gases, will cool down or heat up a little bit when they expand into a vacuum, whereas an ideal gas always becomes. Right? So that's called the Joule-Thomson effect. Measuring it was really tricky, but if you happen to look at this in a thermo textbook, it's how they make things like liquid helium, liquid nitrogen, liquid helium is done through Joule-Thomson cooling of real gases. Okay, there's the answer to all of that. Okay, so everything I just said is just summarized here. Okay, a real gas will change since the distribution of potential energy, kinetic energy changes. In an ideal gas, there is no potential energy. There's just kinetic energy. That's why it doesn't happen for an ideal gas. Now, that's sort of that's the first law of thermodynamics, so we've sort of covered through. We've talked about enthalpy. Here's a real review of high school thermodynamics. Remember these phase transitions. So fusion is when you have a solid and you take it into the liquid phase. Sublimation is when you have a solid and you take it into the gas phase. Imagine dry ice turning into CO2 gas, right? Vaporization is when you have a liquid and you turn it into the gas phase. So these are all processes where you go from these states of aggregation, these states of matter, solid, liquid, and we convert them to the more disordered state, less aggregated state, probably better to say. And those all require energy to do that. So if you go from a solid to a liquid, you have to put energy in to make that happen. From a solid to a gas, energy goes in. From a liquid to a gas, energy goes into the system to make that happen. If you want to go the other way, you got to take energy out, okay? When you do these processes under constant pressure, then the change in energy can be described as the enthalpy change, which is the heat flow that causes this under constant pressure conditions, is what's called the delta H for the transition. Delta H is sublimation, delta H of fusion, delta H of vaporization. Okay? And this is stuff that you probably would have learned about the first time you ever learned about thermochemistry. Okay. Again, something else you would have learned about. Thermochemistry, you learn about reactions, products minus reactants of your state functions. So if you had some chemical reaction like this, you would write down delta H for this reaction as H for C, 5 times H for D, minus 2 times A, H for A, and plus 3, minus 3 H for B. And you put this together, and that's the delta H for the reaction. We often write this in just one summation form, where we write the stoichiometric coefficient, 2, 3, 1, and 5, as this symbol nu, and we make it positive for products and negative for reactants, so we get this correct signs here in that summation. All right, so that's just, remember Hess's law and those kind of things, right? One of the things that you do in thermochemistry, you might take a reaction and you calculate the delta H for the reaction, And you would just say, okay, well, it's just all the enthalpies, the molar enthalpies of the products minus reactants, right? But the problem is the way I've written this is those are all written in terms of absolute molar enthalpies. And that's not something you easily go into the lab and measure absolute energy of. But it turns out there's this trick that you learn about in high school, which is if you take all the compounds in this reaction, so like water and the iron oxide, and you write it as a formation in terms of its elements. So there's this reaction, so the formation of water in terms of its elements is just products minus reactants, and the formation of iron oxide is equal to products minus reactants. And then you rearrange these guys in terms of the absolute molar entropy of water and iron oxide, and you write it like this, and you substitute it back into this expression. Well, then all of these guys end up canceling, and this reaction ends up having a delta H, which is just the difference in the delta H of formations. So you remove this absolute enthalpy, and you're now writing in terms of relative enthalpies, which is delta H of formations. Maybe you remember like learning this in freshman chemistry, and they said you set all the elements to zero, right? Well, that's not quite right. What you're doing is they're canceling out, and that's what you're doing. Okay, so that I guess is really kind of a review. Something you probably don't learn when you're learning about those reaction enthalpies is that they're always usually given at standard state. So they're always given at a standard state of 1 bar, which is P naught means 1 bar. And they're always given at, say, 298. I think 298 Kelvin is the standard temperature. So you look at a table and you get those in the back of the book. There's all these tables. And if you want to adjust them to a reaction that starts and ends at some higher temperature, what do? Because your table's all at 298. Well, you can adjust them up by using the heat capacities of all the substances involved in the reaction. So you can just use this expression here. You can write out the delta H of the reaction. You take the derivative with respect to temperature. You get that equation on the previous slide, this slide, right? This one right here, and that becomes this. These are all the change in the all the molar heat capacities, and you can define this as what we call the heat capacity for the reaction. And then you can use that, if you calculate this quantity, you can use that to adjust any enthalpy from temperature 1 to temperature 2. You take the one where you know it, you do this integral, and you get the enthalpy change for the reaction where you don't know it. Okay? It's a simple sliding it up and down. Okay. There we go. So that's my summary of the executive summary of the first law of thermodynamics as related to chemistry. How you doing? All right. We got 15 minutes. Okay. This is the point where I'd make a new video. Actually, I would have made 3 videos by this point. Let's talk about the second law, okay? And Clausius, I think, says it very, very simply, is that heat is not going to spontaneously flow from a cold body into a hot body, right? So that is the wrong direction. Heat will flow from a hot body into a cold body, but it will never spontaneously flow from a cold body into a hot body. So that's just stating the obvious. But what wasn't known in Clausius' time was, where is that in the thermodynamics? Where is that in the thermodynamic equations? Where's the equation that captures that behavior? Because we need that. We got to make sure that that never happens in our predictions, right? Because it won't happen. If it does, we made the wrong prediction. So this process where if I have 2 sides at 300 Kelvin, if all the heat over here happened to flow over to this side got cooler and that side got hotter spontaneously, that's an impossible process. Whereas the other direction, if I had these 2 guys with a diathermal barrier, where you put them together, they would spontaneously go to that, where they became the equal amounts on each side, the same temperature, right? So what Clausius figured out in 1865 is the actual equations that we needed to add to thermodynamics and make sure that the impossible process is never part of our predictions. We only predict the spontaneous processes, right? And he did this by reading a very small book that was published by a French guy named Sadi Carnot, who wrote it in 1824 and was kind of lost, and they rediscovered it. And he had been working out, because everyone was building steam engines back then, and he wanted to know how to make a more efficient steam engine. And at the time, everyone thought that heat was a substance called the caloric, which is wrong, but actually he used this idea of the caloric to work out the efficiency of heat engines. And it turned out even though caloric was not right, his equations were all completely correct for just on the basis of heat and work. And looking through this book, Clausius realized that he had found the missing function that captures this statement in the theory. So Sadi Carnot designed something called what we now call the Carnot cycle for an engine. And this is how it works. Now remember, I made you sit through me deriving the isothermal expansion of an ideal gas, the adiabatic expansion of an ideal gas. We went through those equations like, oh my God, that was good. The second one, the adiabatic one, was really painful, and we're going to need it, okay? Because the Carnot cycle is this. You have a hot reservoir and a cold reservoir, right? And the way this engine works, the way they visualize it, is kind of like, like a water wheel, in a waterfall, right? So water's coming down, and you're using that flow of water to turn the wheel and generate work, right? So Carnot had this idea that caloric heat was a flow, and heat was flowing from a hot body into a cold body. And if he could put his engine inside, he could capture that flow and create work. That was the idea. How do you do this? With thermodynamics, right? So you imagine you have a piston with some gas in it, and we're going to do this completely reversibly, all at equilibrium. So the piston is in a gas, and we're going to let it isothermally expand at the temperature of a hot reservoir. So it's connected to the hot reservoir, heat is flowing in, and work is coming out because it's expanding, right? Remember, heat flows in, work goes out. If it's an ideal gas, actually the energy stays constant, right? So while this is happening, the temperature is constant, and we're getting work out of the system. But in the next step of the cycle, it disconnects it from the hot temperature reservoir and keeps it disconnected from the cold reservoir. So now it's isolated, adiabatic. And he continues to expand it. So now he's getting work out, but it's expanding adiabatically because work is coming out, temperature is dropping, right? But he's getting work out. He lets it drop, he gets the work out, he lets the temperature drop until it reaches the temperature of the cold reservoir. Then he stops. Then he connects it to the cold reservoir, and then he puts work in. And as he puts work in, the temperature is going to stay constant at the cold reservoir temperature. It's isothermal compression. Heat is going to go into the cold reservoir, and he's going to compress it back to a certain volume, and then he's going to disconnect it, and he's going to take it back, and he's going to do he's going to do adiabatic compression. And now it's at the cold reservoir temperature initially. He's going to compress it. He's going to put energy in. The temperature is going to go up until he gets to the temperature of the hot reservoir, and then he's going to stop, and then he's going to start all over again and repeat the cycle. That is the Carnot cycle. So he's got work out and work in. But the point of this is the net work is going to be positive, and we're going to get, this is going to be an engine. And it's going to capture the heat flow from the hot reservoir flowing down to the cold reservoir, mediated by this engine. And by mediating it, we're going to extract work out of that. Okay? So if I looked at a PV plot, this is all done reversibly, then it looks like, okay, I got isothermal expansion, that was the first step. Adiabatic expansion, that was the second step. Isothermal compression connected to the cold reservoir. Adiabatic compression disconnected, and I'm back to where I started. And so there's area under this part is the work that I got out. The area under that part is the work I put in, and the area inside is the net work that I get. See how easy that is, right? On the PV plot. You just plot the whole cycle, and the area inside is the work, okay? And it's given by this expression right here. Yes?
So do you minimize work if you have the temperature of the container close to the temperature of the container.
Yes, so the greater the temperature between the reservoirs, the bigger, obviously if the temperatures of the two reservoirs are the same, you get no work, right? The bigger the temperature difference, the more work you get, right? That's the kind of things you wanted to know, right? You know, those kind of things. All right, this is the exciting part. So if very simple derivation here to figure out the efficiency of this engine. So if we say that the cycle, which is the heat from the hot reservoir plus the heat from the cold reservoir plus the net work, all has to add up to 0 from the first law, then we can write down that the efficiency is that the work that we get out divided by the heat that we pulled out of the hot reservoir. That's how we're going to define efficiency. So we're taking heat from the hot reservoir and we're getting work. We've got to dump it into the cold reservoir, but the efficiency is this ratio. We put a negative sign there, so it's a positive number there. So if I rearrange this and substitute it back into the first law, for work here, it looks like this, and then rearranging it, it looks like this, which is the efficiency is 1 plus the heat flow of the cold over the heat flow from the hot into the hot, from the cold and then out of the hot. And these guys, remember the signs, the cold is going to be positive because it's going into the system, and I'm sorry, it can never be, this is always, Jesus, sorry. This is always confusing. So the magnitude of the heat flow from the hot reservoir is always bigger than the magnitude of the cold because we're getting work out in the process, right? So if you get the signs out, this number can only be 0 to 1, but it actually can never reach 1 exactly. So the thing is that if you ran Carnot engine backwards, so remember those steps in the cycle, but if we ran it in the reverse order, you would make what's called a heat pump. And a heat pump will take work and move heat from a cold reservoir into a hot reservoir, kind of like an air conditioner, okay? But it takes work. And what Carnot realized was that if you coupled a heat pump and a heat engine together between the exact same two hot reservoir and cold reservoir, that you can make something that violates what we would call the second law, right? An impossible process. So if you imagine I had a heat engine with an efficiency of 1/4 and a heat pump with an efficiency of 1/5, if they had different efficiencies, then I could take the heat engine, which was taking 4 joules from the hot reservoir, dumping 3 joules into the cold reservoir and getting out 1 joule of work, put it into my heat pump, which will take 1 joule, move 4 joules from the cold reservoir and put 5 joules into the hot reservoir. The whole super system of these two would give me effectively something that takes 1 joule from the cold reservoir and puts 1 joule into the hot reservoir without any help, without any work. Completely impossible. So the only solution to this dilemma would be that the efficiencies between the same hot and cold reservoirs have to be identical for all engines. They can't have different efficiencies like this. So that means that the efficiency of the engine depends only on the temperatures of the hot and cold reservoirs. It doesn't depend on the details of the system. As long as you run that system reversibly, it doesn't matter what you're doing in there. The efficiency depends upon the temperatures. And that's what we have to work out. Okay. With those derivation that we did those adiabatic steps and the isothermal steps. We did that derivation already. If you rearrange those equations for those 4 steps, you can see that for the 2 isothermal steps, for the adiabatic steps, we get this expression right here. And I'm going to go a little quickly here, but we'll come back to this. And then for the isothermal steps, we have this term here, where the heat was given by these ratios. And then we can take the ratio of the heats, which is what we need in the efficiency expression, and it ends up giving you this expression. And then using the adiabatic steps, we can cancel these guys out and make it equal to this. And so now we have the efficiency entirely in terms of temperature, and that's why you can't have the same temperature for the hot and cold reservoir because you both have a zero efficiency. Right? So that is where that ends. But now, the last thing I'll leave you with is that Clausius realized that through that process, that the heat flow over the temperature throughout the cycle added up to zero. So in other words, there was this isotherm, adiabat process, but he realized that if you took any cyclic process, you can imagine whatever the shape of that process, I can always discretize it. So it looks like at some point I'm on an isotherm, then I'm on an adiabat, then I'm on an isotherm, then I'm on an adiabat, and I could write the whole thing as a combination of isotherms and adiabats, so that the integral over the cyclic process has to be this, and it has to be equal to zero. So scratching his head, Clausius realized, wait a minute, any property that comes back to zero in a cyclic process is a state function. And no one's ever saw that state function before. dq over t is a state function. So he realized that dq over t is a new property of the system that's independent of the path. It's done reversibly, and that's what he called entropy. Okay? And that is the equation that will capture that statement that heat will never flow spontaneously from a cold body into a hot body, because that would cause the entropy to decrease spontaneously, and that will never happen. But that will be for the next lecture, okay? All right. Congratulations. You sat there an hour and a half of thermodynamics, and I can see any heads on the table.